Thank you for coming to this talk. To kind of level set things, well, let me first say where we're coming from. This work is a work in progress, and it pertains to a project we're doing for OSD, and the acronym is DTE&A, Development Test Evaluation Acquisition. Pretty long title. But may I ask, do we have folks here who are pretty familiar with the developmental and operational test community? Is this kind of new? It's kind of a specialized area. So let me say a word about that, if I may. When the services develop a major new system, they start with some system that's either a prototype or else it's a legacy system, a system that already exists, and they want to improve it. They want to make it better because the threat has changed or it's become expensive to maintain. And there's an institutional way of doing that, and it involves a developmental test program. And a developmental test program requires some planning, allocation of resources, and execution. Now, the work we're doing pertains to that, and it pertains to a particular part of the that process, which is the estimation of reliability. And the estimation of reliability per se is one of many different parameters. If you're buying a system like a tank or an airplane, there are lots of things you're interested in. But we believe that the reliability estimate is a pretty critical part, particularly early in a test program where, if you will, the concrete hasn't set, you have a chance to change your plan, to change the way you're doing business. So you really need to know a lot about reliability and the estimated reliability going in and going along when you want to track the reliability of the system. So that's where we're coming from. And this particular project we're doing for OSD involves trying to address a problem that has developed over a period of years, even decades. And that's this. Now, this is my personal opinion. It may not be the official opinion of many in the test community. But there are methods, and I'm talking more from an Army perspective, being that I'm most familiar with that. There are methods that have been very good, developed by some very smart people within the Army, and particularly the agency was called AMSA. It's changed the name a little bit now. And they've worked well for years. They've done a good job. The problem is the methods haven't changed that much, and the institutional embedding of the methods haven't changed much, but the world and the environment has changed a lot. Testing is now more like half a decade rather than most of a decade. The number of systems tested has decreased, and the complexity of the systems that we're testing has increased. And in my opinion, this has been like the frog in the pot cooking slowly. The frog hasn't realized that it's being cooked, and we continue doing things pretty much the same old way and feeding them to decision makers in the test, and they consume this information, but they know very well that it's kind of chancy. It's not as consistent as they like. So they amend their decisions not only based on reliability estimates, which should be very good, but I call it putting your finger to the wind. It looks like we're going to succeed. And that's what the problem is. And what we're trying to do is address that problem by enabling people who haven't had the time to get familiar with newer and better techniques, and I'm talking Bayesian now, to address problems in estimating reliability for developmental testing. So that's where we're coming from on this. And okay, some help from my technically adept person here. And basically, that next slide that you saw briefly basically says what I just said. It kind of level set the whole situation. And Dr. Fanto now, who's, I told our moderators, he's doing the interesting part of the talk, and I apologize, I follow with the more boring part of the talk. He's going to present some applications based on existing methodologies, material that is in the literature. It's been developed by very smart people over a period of years, and showing that there is real payoff. And that's pretty much what our previous speaker said, but we're going to illustrate it in the context that I just mentioned. So Dr. Fanto, please proceed.
Thank you. And Liz, thanks for your patience with our technical difficulties and for sticking around until the last session here. So as Dr. Spalding said, the goal of this project is to create a framework and set of best practices to encourage the increased use of Bayesian methods during developmental testing, or DT. And so what I'm going to do in the next few slides is just show some illustrative examples of the utility of Bayesian methods with simulated data from a notional system. And specifically, I'm going to apply Bayesian reliability methods for both planning and assessment and compare them to current frequentist methods, and also show how Bayesian methods can include additional sources of uncertainty, such as uncertainty on fixed effectiveness factors. And I should say this isn't new research. This is basically the application right out of the box of published methods, where the papers are listed at the bottom of the slide. And it also represents a very simple application. So I'm sure we have true experts in Bayesian statistics in the audience. This is not the most complex thing that you can do with them. So this slide, I feel a little humbled after the excellent talk on priors, presenting this very simple depiction of the Bayesian process. But as we heard in the last talk, the Bayesian process starts with forming a prior distribution for, in this case, your system reliability, which we quantify through a failure rate or a mean time before failure for a lifetime system. And this takes into account various sources of information available before the test program begins. And then for each test segment, we can take our test data and, using a likelihood function, combine that data with the prior distribution to obtain an updated or posterior distribution for your reliability. And this represents a single segment, but tests can go over multiple segments. And so, again, as we heard in the last talk, we can use the posterior distribution from previous segments as the prior for subsequent segments, and thereby can consistently include relevant information across the entire course of the test program. And so this is a slide that shows in a schematic way how Bayesian methods can improve precision for shorter test segments if the prior is correctly specified, or at least not too inconsistently specified. And so what you're seeing, what the chart shows, is the result of applying Bayesian and frequentist methods to simulated test data for a system with a ground truth mean time before failure of 40 hours. And the results of the analysis methods are shown for differing lengths of the test segment. And so what you can see is that the Bayesian methods shown in orange are more precise if the test segment is shorter, if there's less data to work with. And that's because the prior distribution constrains the maximum value of the MTBF to a relatively reasonable range, whereas the frequentist method in principle is allowing any possible MTBF to be considered. However, if you have enough test time, you can see that the two methods eventually produce identical results. The test data has totally overwhelmed any prior distribution. So another useful method that's available in the open literature is a Bayesian method that enables the inclusion of uncertainty in a reliability growth curve. So, as I'm sure many of you know, DT programs project the expected growth of the system reliability over the course of the test segment. And this is in standard methods is typically represented just by a line. And what this method, which is published in the paper listed there, allows is by assuming a certain prior on the initial system reliability, and then also assuming the expected improvement in the system's reliability, one can obtain not only the average reliability growth curve, but also an uncertainty band, a confidence interval or a credible interval around that growth curve. And this can be very useful to know if the system's improvement is way outside what you might expect, or if it's within, it might not match the growth curve exactly, but it's within a somewhat reasonable range. So now this actually shows, again, a notional application of Bayesian and frequentist methods to simulated data for a full multi-segment test. So here, again, this is just a generic complex system. I assumed that there were 5 100-hour test segments and simulated failure data from an exponential distribution, and then applied a current standard frequentist method and also a Bayesian method from the paper listed there, which assumes gamma prior that's probably weakly informative. All it does is set reasonable bounds on what the MTBF should be. And what you can see on the plot is that the Bayesian methods, shown in green, have 2 advantages. One is that, especially for the early segments, they're more precise. Your uncertainty bounds aren't quite as wide. But the other useful feature is that they capture the overall trend. The system's reliability is, in fact, improving. And if you look at the point estimates, the Bayesian point estimates, they are improving as well. Because they're including all the data from the test program, they're seeing that the reliability is increasing on average. However, the standard method, which only considers data from each test segment individually, fluctuates and in fact decreases before increasing at the end. Now, finally, before wrapping up this section, I just want to show that Bayesian methods can very naturally include additional sources of uncertainty, such as the uncertainty in the fixed effectiveness factor, or the average improvement in the system's reliability between subsequent test segments. And this can be included just by introducing a new prior for each fixed effectiveness factor after each test segment. This makes the posterior distribution somewhat more complicated. It can only be visualized by applying a Monte Carlo method to sample the joint posterior of the failure rate and the fixed effectiveness factor. And as you can see, the figure shows the marginal posterior distribution for just the failure rate. And as the segments increase, this distribution moves to the left and becomes narrower, meaning that the failure rate is both decreasing, the reliability has improved, and our estimate of it has become more precise. And then finally, we can also see obtain some information on what the fixed effectiveness factors were for each test segment. So in this case, a uniform prior was assumed for each FEF. The figure shows the marginal posterior distributions for the fixed effectiveness factors applied at the end of each segment. And as you can see, we've gained the most information for the fixes applied after earlier segments. And that can be shown by the difference from a uniform distribution. And it makes sense because the early fixes influence all later test segments. So we effectively have more data to evaluate these factors. And so to conclude, I hope I've convinced you that Bayesian methods can be useful for DT programs through illustrative examples using notional data. And so now I'm going to turn it back over to Dr. Spalding to describe the framework and best practices that we're in the process of generating.
Thank you, Paul. A couple of points I should have made a little bit earlier. The purpose of the work we're doing for OSD is to end up with, for lack of a better word, with a handbook that can be used by practitioners who are very busy and have been using the same methods for years. They're not necessarily unsmart. In fact, some of them are very smart, but they don't have the time and the institutional, if you will, top cover to change the way of doing business. And what we're trying to do is create a handbook that will inform them and give them some options to improve their analysis. And in my view, I don't know how this, frankly, I'm not sure how you all receive what Paul just said, but every one of those charts pertains to some, if you will, some rather painful incidents I've experienced over the years in terms of what is the trend of this thing. We did tested this thing, we're halfway through the program, and we got a low point. It's been doing great for the first 2,000 hours, and all of a sudden we got a low point. What does that mean? And the smoothing is important for that. And Paul's point about getting better fixes on the, pardon the dual use of the word, better understanding of the reliability early on, goes to my point about that's when the concrete isn't set yet. And that's when one can best influence the further execution of the test program. So this looks kind of academic, and it looks kind of been there, done that, maybe as an undergraduate, but it really does relate to real cost and schedule, real cost and opportunity cost in real programs. So I just want to thank Paul for having the patience to go through all of this stuff for the project. Now I go on to the next slide, which okay, there we go. I got it. Okay, right arrow. There we go. Wonderful. Well, I'm going to go at a very high level. And how many minutes do I have left?
15.
15 minutes? Okay, that's great. Okay. What I'm going to do is describe a very simple, methodical, and almost intuitively obvious process for putting together a story that would fit into this handbook I'm talking about, and for which a practitioner can draw some useful information and get to a point where she or he can pick a model and explain it and use it. All of those are important. So I'm going to talk about, first of all, what is the problem that I'm talking about, that I'm trying to solve? What are the possible solutions? What is the context, and I call it a framework for thinking about all this. And finally, what are the best practices for actually applying something that you've identified in the context? So what we want to do, and we're in the process of executing this now, is to first get the low-hanging fruit with as little pain to people we want to poll. We want to find out what the community thinks the problem is. And we see the problem as, what is it about the reliability estimates that are done for you, the decision maker, or done by you for the decision maker? What is it that you think are sore points that need to be improved? And I give a couple of examples in this notional chart here, which is one, unreasonably high goals for the program. And the reason they're high is because the way things are done now, they're very uncertain. And if you want to buy some insurance of meeting the requirement, you tell a contractor you have to do very well. So that's one example. And you get asked this, requirement's only 100. Why do I have to ask the contractor for 200 or 160? And the answer is, you don't know the uncertainty well enough. Another example is what's the initial reliability of a prototype that you're feeding into the system? Why is that important? Because the whole plan, in very large measure, depends on what you think you're starting with. And if you get it right, that's great. You get a plan that you can probably do pretty well with. If you're off by a factor of 2, and in this success-oriented environment, that is not impossible, maybe not even infrequent. You find out about it towards the end of the developmental test program, and that's kind of late. And that, in the end, it costs you just as much to do things that way as if you had planned a little more carefully to begin with. So those are two examples, and that's what I mean by an issue. And we're going to poll for those at a top level, and then we're going to explore those with interviews with subject matter experts. We want to know the whys and the hows, and we also want to know what data is there out there that nobody is using, is available, and why it's not being used or why it's not available. And we want to understand that. And that's what I mean by defining the problem. Now, what are the solutions? Well, as implied by Dr. Fanto's presentation, we're not going to try to invent new solutions. They're out there, and we're going to rely, like anyone starting out with a doctoral thesis, on a search of the literature of the people who know the most about the subject. And if I can put in a plug for our program, we might even ask AFIT to give their opinion on the subject. What methods are there out there? What are published? And Dr. Fanto gave you a couple by a very capable statistician at AMSA in the Army. Having done that, we want to be able to characterize these different models. And the stereotypical, and we may change this depending on the inputs we get, developmental test program segment has a plan, it has a beginning, it has a middle, and it has an end, which is a very simplistic way of saying it. But different models apply at different points depending on what the issue is. So characterize it that way, and we want to characterize each of the issues not only that way, but what are they good for? What issues do they address, such as do they calculate initial reliability well, and what are their assumptions, because that'll feed back later into whether you can use them or not. In addition to that, they work great in principle, but what kind of data do they need? Will the data be available for a typical program? So that's what I mean by identifying and characterizing solutions. And we want to put them together for context. And this is really a great simplification. But again, this is for the busy consumer. It's not necessarily for this audience. It's very simplistic. But you play the solutions against the issues. And they fit somewhere in this rubric here. And the color of the box indicates how well we think the solutions will do generically. And underneath that box, if you were to click on it figuratively, you would find a model or a set of models and a careful discussion of what their assumptions are and what kind of data they need in order to work against the particular issue of interest. So at this point, if you are a consumer of all this in this handbook we're developing, it's like you have a very good friend who's all meeting and says, why don't you try this for your problem? And your response is, I'm kind of busy. He said, I'm really not sure how I can use this thing and whether it's really going to work or not. Sounds interesting. So a necessary follow-on to that is to get into the nitty-gritty of how to apply a particular set of models that you've identified might be useful for the issues that are bothering you at the beginning of the program. It may be the initial reliability. It may be the uncertainty and how to describe that to decision makers who really don't want to. That's one more thing. You're making my head hurt. You mean you can't be sure this thing is going to come out to meet the requirement? How to deal with that, describe it numerically, and possibly rationalize why it's there. And what I've shown on this chart in the horizontal direction is what I consider to be the real world on the left, and on the right, what I consider to be the orderly, rational, incisive, sound world of statistic methodology and the models that stem from them. And what we're attempting to do is to provide the means for the analysts to connect those two. And the real world, as I think maybe everyone in this room understands, it's messy, it's complicated, it's arbitrary, it's constrained, and has all these things and a lot more probably than we hope to identify. Just one example, let's see, some of my favorite ones are, not do you have the information, but when is it going to show up? You know, when are these fixes going to happen to the system, and when will they be evaluated? If you get all that good information at the end of the program, you needed a production decision before that point, after the production testing is done, it's too late. And that has to be considered in terms of what model you're going to use to inform that decision that's back before the end, the production decision, milestone C. So that's one of many. And how does that match up with the model that you want to use? Is the model, can it stand that? Can it stand uncertainty in the fix effectiveness? Can it stand expert opinion on what fixes will work, which is typically what is really available at that point? And the same with data. It's nice that the data might exist in a program, but who owns the data? What form is the data in? Typically, I can get all the data I want about a predecessor for a system that's undergoing what has been called an engineering change proposal, which is take the old system and just fix it up a little bit using known technologies. The data's there. There might be decades, a couple of decades of testing of the first version, the second, the fifth. But where is it? It's in some database, carefully maintained, but what's the definition of the elements in a database, and what's the context? That's a lot harder to talk about. And that's all a consideration as to And in fact, if you're talking about priors, we're going to use that for a prior. So I consider this chart and the chart about interviews to be the meat of what we're trying to accomplish. Everything else is kind of connective tissue for all of that. And I think we can pull it off, and of course I'm confident we're going to do it well. I think that'll be a real contribution. So my bottom line is simply, we want to be an enabler through this handbook that we're developing for OSD, DTE, and A, an enabler for practitioners to look at Bayesian methods, understand, be motivated by the examples such as what Dr. Fanto said, and to be able to choose a model that would actually have prospects of working, and not least, I stuck that somewhere in one of the charts, not least, not only does the analyst have to understand it, it has to be explainable to folks, and I don't denigrate the people who run the show, the senior officers, lieutenant colonels typically, who run the programs. They may be engineers, they may even be graduates of method with doctorates in it, but they don't have time to get into this nitty-gritty. So the method has to be understandable. So when I talk, forgive me, if I talk about a non-informative prior, I don't need non-informative stuff. Give me some information to react. You're making my head hurt. So there has to be understanding as well as everything else. We want to convey this in a usable, it's not a textbook for a year course, a usable manual that will get the main points and the real important resources in front of the analyst. And that's our bottom line. Thank you for listening. Are there any questions? Well, Mr. Moderator, thank you very much for introducing us. I appreciate the opportunity of mentioning this. I try to show some enthusiasm. I really am. I have some heartfelt feelings about some of the problems I've seen over the last 10 years and trying to somehow get our sponsors in OSD to work with them and provide. By the way, OSD, as you probably know, is an oversight organization. And they're not the policemen, they're there, believe me, they're there to help. We try to help.
I have a quick question for you, either of you. I've never seen that analysis on the fixed effectiveness factors before. I thought that was very interesting. I was wondering, is that novel, or did you get that from somewhere? I thought that was, is there an IDA pub? I'd love to see more of that.
It was inspired and I think largely modeled on an IDA publication that was done a number of, I think in 2015 by, I think Cassandra Franzik and a number of co-authors. And so yeah, it's not like everything, I apologize that I didn't put the reference up there, but like everything else in the talk, it was more of an illustrative example of a method available rather than a novel thing.
Thanks for that. Let's thank our speakers one more time.